We're back. Let's take a look at mechanics. Okay, this is where we're going to start with scalars, vectors, and things like that. All right. I'm starting at question 14, where we say define a scalar and a vector and explain the difference using some examples. All right. Well, first of all, let's just let me put myself back onto my. I am already on it. Okay. So let's just have a look. What is a scalar? A scalar is just a magnitude, isn't it? It is a magnitude only. In other words, it's an amount. How much? Okay? A scalar is how much. Okay? It's just a number. Okay, put my E in. It's a number. Okay, so then what is a vector? Okay, well, a vector is going to be the magnitude. Okay, the magnitude, which is how much. Okay, plus a direction. Which way? Okay, so the vector is giving us a magnitude and a direction. So it could be that way with an angle, or it could be northwest, or it could be southeast, or it could be a bearing 214 degrees. Okay? All it is it's telling us how much and which way. I am pulling this that way with 10, or I am lifting it with 10. That's the magnitude is the 10, the direction is which way are we going. All right? Velocity, okay, velocity, speed is a number, 60 kilometers an hour. The vector is 60 kilometers an hour north because it qualifies which way you're going, okay? That's the difference between the two. So if we see a signboard that said town X, 25 kilometers, that is a scalar. If we see a signboard that said town X 20 kilometers that way, that's a vector because it's telling us a distance and a direction, is it not? Okay, so here's one for you. What's time, a scalar or a vector? Can time go in a direction? Time can only go forward, can't it? We can't go backwards with it. But I suppose you could call it a vector because it's forward, okay? Well, the whole time travel thing, don't know. That's another debate, isn't it? Right, let's have a look, okay? Just, giving some examples quite. What is the difference between distance and displacement, right? Let's have a look. This is question 15. Distance and displacement. All right. What is distance and what is displacement? Well, distance, remember, displacement is what? How far from the origin? Okay. How far am I from where I started my journey? That is my displacement. So my displacement can be 0, but my distance can be 100 kilometers. Because if I started here and I did all of those, remember, what we say is right, let's say we start here. That is our origin. And we go this way, then that way, then we go up there, then we go up there, then we go up there, then we go there, then we go there, then we go right down there, and last we go right back home. The distance is adding all of these together, all right? That's the distance. So the ticks is equal to the distance. The displacement is equal to 0. So somebody could say to you, if essentially you haven't done anything because you haven't moved. You're still where you were. But you did all of the laps, all of those meters or kilometers to get back to 0. Displacement, thus, is the distance from an origin. Okay, it's where you actually are relative to your origin, and your distance is your sum of all of the individual distances that have been traveled, correct? Right, okay. The other thing, of course, displacement is a vector, okay? Distance is a scalar because displacement has a vector, okay? Let's just have a look here. I was here, this is my origin, and my displacement is there. Therefore, if my displacement is there, this is my displacement over there, and it's got a direction. North, east, south, west, whichever way it is, correct? Okay, that is those. Okay, let me just get myself back to my color. Okay, then the next question is this, all right? They're going to explain the concept of a resultant of a set of vectors and explain the concept of equilibrant by using an example again. All right, let me just create a new page over here. All right, a resultant and an equilibrant. Remember, the resultant is the result of all of those vectors acting. So therefore, okay, so what do I say? We say, okay, therefore, a resultant is the end vector sum of the vectors, isn't it? So we say, right, here we go. Let's say we went there and then we went to there like that. We added them together, all right? And we end up with a resultant like that, right? Remember, the resultant is the unbalanced one. It's the unfinished bit, if you like, right? So when you've got the set of vectors, you find the resultant, you add them vectorially, nose to tail, or you do it via components, okay? Which, if we haven't got there by now, that's still coming as well. So what we're going to do is we're going to say, right, we add them all. The resultant is the origin to the last vector. There it is like that. And it has got an angle over there, so it's a vector, all right? That's the resultant. In other words, if somebody pulls you up with 20 and along with 40, you're going to end up going that way, aren't you? Your resultant is in that direction, right? What is then the equilibrant, right? The equilibrant is the exact opposite to the resultant. It's the exact opposite acting at theta. That must be equal, and R is equal to E. Okay? The equilibrant is the force which acts in the opposite direction with the same magnitude as the resultant. In other words, if you had a resultant which is going to tend to make us take off that way, the equilibrant is the force that's going to keep me back. It's exactly like that, right? So I've got my resultant and the equilibrant down there, okay? The equilibrant is the force that is keeping me back, all right? Now, next one, they say, find the resultant of the following set of vector if there is one. What do they mean, if there is one? Well, there might not be a resultant. Remember, the whole thing, I might not have a resultant displacement if I've come back home, all right? I might have a whole bunch of forces acting like that, okay? And they end up closing. So the origin and the last one goes to there. There's no resultant. Doesn't mean you haven't added them correctly, just means there isn't a resultant. In other words, all the forces actually balance it out. It's in equilibrium, isn't it? That's what's happening over there. All right. Now they say, using a scale diagram of 1 centimeter equals 10 newtons, do the following. All right. In other words, they're asking us to draw a scale diagram. Right. Now, for those of you who are not doing geography, okay, or EGD, this is it's a different concept altogether, because you've got to start using scales and things like that, right? And plotting angles, etc. So what have they given? They've given a whole bunch of information. They've given directions, okay, and magnitudes of something, all right? So what are they saying to us? They're saying, right, Let me just go back to my thingy. They're saying, right, the scale is going to be 1 centimeter equals 10 newtons. Now they've told us 40 newtons to the right. So what do? I say, all right, I go 1, 2, 3, 4 centimeters, because that is a diagram. 4 centimeters is equal to 40 newtons, right? Or how would I work it out? You take your scale and you say 1 centimeter equals 10 newtons. And we know it's going to be 40 newtons. How much is that going to be? So we say x. So 10x is equal to 40. X is equal to 40 over 10, which is 4. You can always, when you've got the scales, use the cross multiply to work it out. So that is going to be 4 centimeters. All right. Then they say 60 to the left. Okay. All right. 60 to the left. Okay. Now I'm going to change color and I'm going to go 60 to the left. So I'm going to go 1, 2, 3, 4, 5, 6. I'm going to go this way. So there we've added that in. Can you see? There's the nose to tail. So that's 6 centimeters to the left. Okay. Then they say 50 vertically. All right. I'm kind of going to be going over my own diagram. So what I'm going to do is I'm going to do the 100 down. Okay. I'm going to have to put in more lines here. 2, 3, 4, 5, 6, 7, 8. I need more. 8, 9, 10. So then I say, all right, here I've got it coming down all the way there. This is 10 centimeters going down, isn't it? Then they say 50 newtons vertically upwards. So now let's go. The next one is 10, 20, 30, 40, 50. So my next vector goes up to there. And that's where I stop. This is my end. All right. I'm just going to scroll it back. All right. So let's just start off. Come back. There we go. This is over there is the origin. You always label the origin and the end. And what's the last thing we say? The last thing we say is okay, we have got a line to join them. So I'm going to say, right, it's a line joining there to there, right? Like so. All right, let me just hide my pencil toolbox. And this I can call my resultant. Oops. I didn't put my pencil back to where I wanted it. Okay, switch that off. So therefore, I'm back to there. And this is my resultant, isn't it? How do I work out what it is? Well, what do? I do this. I measure centimeters. Then I use my scale. 1 centimeter is equal to 10 newtons. When I measure it, I get 5.4 centimeters must be x newtons. So cross multiply, x must be equal to 54 newtons, correct? And if I need the angle, all right? So what do? I measure, let me just get a little thingy here. Okay. I measure angle theta with a protractor. Okay. I measure it with a protractor and I'm going to get 70 degrees. Okay, on the measurement. Okay, now I'm going to put in here, because what you can do is do this with components when we've done the components, and the exact answers are 53.85 newtons and at 68.2 degrees. All right. So you can see that our measurements and our thing, we're going to be, because it's the thickness of lines, getting the angle 100% right, blah, 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 blah. All right, this is not an exact business, all right, but we're doing the best we can with what we've got. Let's have a look and say, all right, let's have a look at question B now, all right. Okay, I need to put another page. These are quite paper consuming, as you can see. Let's have a look at the next one. They say, oh, they've given us 120, 30, 10, 20. And they say, using a suitable scale, do it, all right? So once again, you'll pick a scale, right? Hint, don't pick a scale. And the only way to do this is practice. There's no other way. You actually have to get a feeling for where to start, that you're starting not too far left or too far right. Just practice a few. It actually comes very fast. So what do? Well, we are going to say this is our origin. Oops. So let's say this is my origin here. All right. I am going to go 1, 2, 3 that way. All right. There's my first vector. That is my 20. Sorry. Let's say it's to there is my 20 Newton vector. Okay. I'm going to delete this now. Okay. There we go. That is 2 centimeters. Then I'm going to go 1, 2, 3. All right. And you're going to see in a few minutes, I'm going to run out of space. All right. I have started too far to that side. So what do I have to do? Unfortunately, I've got to go and I've got to restart or just join an extra piece of paper onto it. Okay. So let's just start in the middle here. Let's put in our first is 20 newtons, 1, 2, 20, 2 centimeters that way. Now I must add in another vector. Okay. Let's add in, hang on, let's keep all of those that color. So now I've got to say I'm adding another 1, 2, 3. There is my 3 centimeter, 20 Newton and 30 Newton, right? Now I've got 100 Newtons to the opposite direction. So I'm going to just put those in. Now I say I must add all the way is 5, 6, 7, 8, 9, 10. So my vector goes all the way to there, doesn't it? There is my 100 newtons, which is 10 centimeters going that way. Now I must put in 10 down and 20 down. Let's have a look. There's 10, 10 down, and now I must put in another 20 down. Okay, so now where are we? Okay, let's go back. Okay, always label origin. Like that, always label the origin, okay? And therefore we say to ourselves, we do that and we say, okie dokes. Now, I want my pencil toolbox and I want to do that. And I'm going to say, right, this is my resultant, isn't it, over here? And it goes from, finishes, and what do we say? The resultant, I measure it and I get 5.9 centimeters. 1 centimeter equals 10 newtons. Therefore, I measure 5.9. We need x. Cross multiply. Like that, right? X is equal to 59 newtons. It's on that side. So my resultant is 59 newtons. And the angle theta, okay, that I measure is I measure theta down that way, and I end up with 31 degrees south of west. All right. And now, if I did this exactly, I would have got, let's put it in, I want it in red, and I don't want my pencil toolbox. I want the exact is going to be 58.3 newtons, okay, and 30.96 degrees south of west, okay. There's some of our vectors there, all right. Okay, let us see. Oh, yeah, we can still do the next one. The next one is question C. The following vectors are all bearings. What's a bearing? Can you guys remember what a bearing is? Okay. A bearing is what pilots use, isn't it? Okay. A bearing is always measured from north. So you always put north and you measure a bearing that way, right? Okay. So this is going to be 90 degrees. This will be 180 degrees. This will be 270 degrees. And a 360 degrees means keep going north. Okay. So what they've now given us is they've given us a couple of bearings. All right. And on this one, bearings are all from the north. So let's have a look. Okay. Right. The following vectors are all bearings. 15 newtons at 0 degrees. What do they mean? Well, first let's draw the darn thing. This is question C. Oops. Hate it when it does that. 15 newtons at 0. Right? That's a bearing of 0. 30 newtons at 270. 10 newtons at 180. Okay? And 30 newtons at 90. Okay? That's 90. That's 180. And that is 270 degrees, right? Obviously, in between there's other bearings, right, that we get. Now, what do? Now we add that as a vector diagram. Well, what are we going to get? Let's just have a look at our vector diagram, shall we? Let's plot it. I'm going to go 15 up. Let's change the scale. Let's make our scale a little bit bigger, just for the heck of it. Let's say that was 10, 15. I'm going to double the scale. So I'm going to say, right, that's 10 there, which means 15 is up there, right? 15, right, is 15 newtons there, whatever the scale is, all right? And then I must say, right, down I'm going to go 10. Hold on. Down I'm going to go 10. So that's going to be down to there, right? There's my 10. Remember, that was 15. Now I've got to go 30 across to the right. Okay, that's going to be, it was 4. It's going to go, okay, 30, right, over there. But hold on, 30 is going this way. So I'm going to say, right, I must put my other 30 in. Oops, sorry. Let's just put it to blue. I must put my other 30 that way. Green was 30 that way, right? And so I end up there. Right? So what is my resultant in this case? All right. My resultant is basically that bit there, isn't it? There. Okay. So if you go and work it out, you're going to find that you get a resultant of 5 newtons . 5 newtons at 0 degrees. Why did I do that? Okay. Because it's a bearing. Okay. We were given a bearing, so we must answer as a bearing as well. Okay. Yep, that gets us to that one. Question 18 is next, which is, they're slightly longer and I don't want to push it too much. So in essence, when we are given this, just a hint, all right, when you have to pick a scale, all right, it really and truly, the only guidance I can give you is just pick something like 1 centimeter 10. Get your lines to be like these lengths so that you can fit on a piece of paper that size, right? Just have a look at it first and see how much is going this way and how much that way. It's a good feel. The whole point about getting into this is actually getting into drawing it. I know that I'm going to preach to you continuously in the sessions we do and in these. The only way to do these is draw, 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 draw. Not only this, physics, draw it. Okay? We're going into mechanics now. Mechanics is where things hit things. Things explode from each other. They go up hills. They get pulled. They get accelerated. You have to draw it. Into next year and the year after, when we end up with momentum and energies, drawing it is the way to go, right? Because it puts everything into a picture. You remember the circuits? What did we do? We put all our information back onto the drawing because that helps us with the next. It's like a geometry problem in maths. What do? You put the angles you've solved for, or the arc lengths, or whatever the thing is, you put it back on because it builds up the picture until it's final. By starting to draw these now, I know for many of you it's a pain, but by starting to draw them now, you are actually pushing yourself so far ahead in the process, you won't believe it. But trust me, you are. You're getting to understand vectors, directions. You're getting a feeling in here of what they're really doing and what they're looking like. You're going to find that you look at something and you say, no, that can't be right. You're building up an instinct for the problems. That in physics is, you know what, that's probably worth 10% on its own. Just having that gut feel is to say, oh, hang on, that's going to somehow look like that because I've seen it before. Please do the drawings. Cheers, guys. Have a good one, and we'll come back and we'll carry on with mechanics. Cheers. Bye.